Welcome, everybody. So you can't see that, but outside my window here in Denmark, we have a fierce blizzard going on. So fortunately, it's we're doing this indoors. What I'm going to take you through here is how you use load response and lifetime in windPRO. I have a presentation first here to set a foundation for you to understand what goes on. You could say behind the user interface in windPRO, and then I'm going to shift to windPRO and demonstrate to you how you use it, and it's actually very easy. So on this first slide, there's a number of logos here, and this is just indicating that we have worked quite intensely within this field of structural engineering and loads for a number of years at EMD, and we've had industrial postdocs and PhDs working on the topic, and we've had a good collaboration also with the Aalborg University, which is a leading university in structural engineering for wind turbines. So I'll dive into the topic. So first, let's look at the question: why do we need load assessments? And so what I've lined up here is the requirements that we have in the IEC standard, the design standard for wind turbines, which tells us that we need a site assessment before we can actually figure out whether a turbine is suitable for a site or not. So it tells us that we need some measurements of the climate on site. We need to simplify this climate into some, let's call it a simplified IEC wind climate. And then we can compare this climate against some design climate. This is called the assessment of structural integrity by reference to wind data. But this is what we call these IEC site checks, which you are familiar with. And if they are all okay, well, we have approved the structural integrity. The case is that this is really not the case very often. And in fact, so very often you would end up with a situation like you see here on the left in site compliance, where you see some checks are okay, they're green, some are sort of borderlining, they're yellow, and some are critical and red. And I would say that in 99% of the cases, if all are green, it's most likely that you have actually chosen a turbine which is too strong. It's going to be too expensive to be feasible for the site. So we need actually, in 99% of the cases, to have a situation where you could say the check just on the wind climate is inconclusive. So we will end up in a situation like this. And in that case, we need to proceed. And the standard tells us that we need to assess the structural integrity by reference to a load calculation. It means calculating loads for the different turbine components and checking if the loads are okay. Well, this could result in something like this, where the loads are okay for all components, or like this. And this is what you'd be seeing in load response. So this is the whole purpose for why we need load response. And the situation could be like this, where you see a yellow check where you have a partial exceedance for the wind speed distribution for some wind speeds or for the turbulence. And it's very difficult to evaluate just by looking at this, whether the margin that you have at some wind speeds compensate for the exceedance that you have at others, and the margin for turbulence compensates for an exceedance, for instance, at air density. So we need the load calculation, and in windPRO we use load response for that. Load response allows you to perform an independent load assessment. So you don't need a manufacturer. For that purpose, we have generic turbine models. So those are models which you can apply generally. This can allow you to select an appropriate wind turbine class at the very early stages of your project development. However, at the later stages, you can actually do a final fatigue assessment also using load response. That is, if you are either a manufacturer or the manufacturer has provided you a specific load response file, so you can do the actual load calculations using the actual turbine model inside site compliance and load response. But you can also do lifetime analysis according to the DNV GL standard. And this is closely tied to the way that we do load calculations. And this is you could say, the main topic here today. But we need to step a bit through the load calculations because they are tightly integrated. So one thing is that what do we actually mean by load calculations, and in this case, fatigue load. So there's a list in the standard that splits load calculations into a number of design load cases. I've highlighted the important ones here, which relate to fatigue. The first one, design load case 1-2, is what we call power production. So this is what wears the turbine down, you could say, in 98 or 95% of the time. That's the main driver of fatigue. There are 3 other cases which are also significant here, and they relate to startup, shutdown, and parked. We bundle these and call these DLC other altogether. These are the so-called design load cases which we cover in load response. And what is load response? Well, load response is a smart way of doing load calculations. It's called a response surface method. I'll not go into theoretical details here. I'll just mention that it's called a central composite design. And what it needs to capture is what are visualized here. So this is a load sweep analyzing how does the fatigue loads depend on the parameters wind speed, turbulence, wind shear, air density, and flow inclination. And you can see, so this is you could say the shape of the load response that our response model, like the one we have in load response, needs to capture. But this is for the blade root bending moment. So when we talk about loads, you could say a main result is what we call the load index. I want to just describe to you what this is. And basically it is when we take this response surface method and we calculate loads for a site climate. So that is, you could say, the result of a site compliance calculation. You get what we call a damage equivalent load, a DEL. In this case, I focus here on the design load case 1-2. We can also apply that to the design climate, and that's what I have here on the right side, and we will get sort of what represents the strength of the wind turbine. And when we take the ratio of these two, we get the load index, which will tell us where the site loads are above or below the design loads, or what represents the strength of the wind turbine. For a generic turbine model, we don't know the actual strength, right? So we need to calculate the loads for the design loads for the turbine by applying the load model to the design climate. This means that it's assuming that the turbine is designed to the limit, that doesn't have additional strength, or what we call margins. This might be the case for real-life turbines because they are part of a general platform where you reuse components for different turbine models, or because other design load cases might actually determine the strength of the turbine. So, and I promised you lifetime, and I'm still talking about loads, but that's because there's a very close relation between the load index and the lifetime, and I'll get back to that in a couple of slides. I just want to mention, because I also mentioned before that we include the other design load cases, what we call DLC other, and this is just showing you how these are included in the calculation of the load index. The factor M here is what we call the Wöhler exponent, which is a material parameter, and I'll get back to that a little later. So I mentioned that manufacturers can actually implement their own turbine models. So how does that work? Well, we know manufacturers, they are very secretive, need to keep their information in-house. And so if they want to implement a turbine model, they need to get a recipe from us. And basically it's a list of 25 different climates that they need to simulate loads for using their in-house tools. This is all going on in-house. Calculating load time series, which they also post-process using their in-house tools to get damage equivalent loads, which they save in a particular format, also specified in this recipe that we have. And these files you can actually point to in a small tool that we have inside windPRO, which will wrap them up and turn them into a load response file, which can then be used to perform load calculations in load response. And this file can also be shared, so it needs to be physically on your computer. So this small tool also encrypts the file, and it can also license protect it. So this is this adds a number of security levels, which makes it safe for the manufacturer to share the file. Yes. So you can either, if you're a manufacturer, you can implement your own turbine models, or if you are not a manufacturer, you can actually request this from a manufacturer. It could be a part of a tender that you request them to provide you a load response file for a particular turbine model. So with this, I think we are ready to proceed and look into lifetime and lifetime extension. So there are some dedicated standards for this, and to my knowledge, there are 3 main standards out there now. There's a DNV-GL standard and there's a UL standard, which have been released a couple of years ago. And then we have an IEC standard called -28, which has not yet been released. So we have a preference for this DNV-GL standard. It's a very concise standard, and it's also freely available. So in our opinion, this is a much better standard than the UL standard. We also are part of this -28 working group, and also the IEA Task 42, which are providing input for these future standards. But for now, we think that the DNV-GL standard is the go-to standard for lifetime extension. So we have aligned the calculations in load response with that, and that's what I'm going to take you through now. So the DNV-GL standard splits the lifetime extension assessment in 2 parts: an analytical part, which is just calculations, and a practical part, which is inspections. And to my knowledge, in all countries, the practical part is a requirement for a lifetime extension. Of course, we can't implement this inspection in our software. So what we focus on is the analytical part, the calculations, which you can do as a very cheap pre-screening to investigate whether it makes sense to proceed to invest a significant amount into proceeding into these inspections of the turbines. So the analytical part in the standard has split into 3 approaches, which is called the simplified, the detailed, and the probabilistic approach. So the simplified approach relies on the use of generic turbine models, just as I described that we have in load response in windPRO. And this is what you should do if the actual turbine model or design is not available. The price is that you also need to quantify the uncertainty from using the generic model. It's not used for anything, it's informative. The second approach is called the detailed approach, and this is what you can do if you have a specific turbine model. So this is what you can also do if you have the specific model available in load response. In that case, you don't need to quantify any uncertainties. The large approach is beyond the scope of windPRO, so we have not implemented that. We have in-house codes for that at EMD, but there you need to account for all significant uncertainties, and you will be doing what is called the full structural reliability analysis, which is actually quantifying the probability that the turbine will fail in any year of its operation. And the design requirement, which is fundamental to the standards, is that this probability needs to be equal to or less than 0.5%. So you could say the last year where the turbine is allowed to operate is the last year where this probability of failure is less than 0.5%. So we cover the simplified and the detailed approaches in load response. And one thing I'd like to emphasize here, when I say a lifetime, it is always implicit here that we mean fatigue lifetime. So it's lifetime within the calculation framework of fatigue. Because in the standard, there is no requirement to assess extreme winds, for instance, because they were assessed when the turbines were installed, and that will still hold. The analytical calculations do not account for wear, corrosion, or abrasion. That is all a part of the practical assessment where the turbine is inspected from the outside. The lifetime here means fatigue life. So again, load response, we use this response model, and we have the generic models, and you might have access to a specific model. Either you have made it yourself if you're a manufacturer, or you have received it from a manufacturer. So what is the relation between load index and lifetime? And this is what I've given here. So it's relatively simple albeit very nonlinear relationship. So this ratio here, the damage equivalent load for the site divided by the damage equivalent load representing design, this ratio is the load index. And when that is raised to the power of minus m, where m is the Wheeler exponent, this material parameter, where we would have 10 for fiberglass, and multiplied to the design lifetime, you get the estimated lifetime for the site conditions. So this is the relation between design lifetime, a load index, and lifetime for a site. And this is the normalization load, which I already touched upon previously. And I'd like to emphasize again that for the generic models in this simplified approach, we need to calculate this from the design climate. So we can't account for any margins. We don't know if the turbine has some additional strength in any of the components. And that can vary somewhat from different manufacturers. The approach, this normalization load is provided from the manufacturer and will include margins. So that is additional strength in some of the components. And just a small note here, you might wonder, does it actually work using a generic model? And it actually does, and very often it is surprisingly accurate. And the reason is that what we are looking at is not predicting absolute load. This is a ratio between the site loads and the design loads. So if we wanted to use a generic model to predict the absolute load levels, we might have errors in the order of 30%. But it turns out that these errors will be very close to the same also when you apply it to the design climate. So they will cancel out. And very often you can see a very high accuracy from using a generic turbine models for this reason. I just wanted to emphasize this, because it might seem a little magic that you can actually use a different load model to calculate loads. Oh, I think it's enough of PowerPoint. So let's dive into to windPRO. And so what I have here is a project, and this is a sample project. So if you wanted to try this out for yourself, you could go to Data and windPRO Samples, and you can download this new Salem, which is a site in North Dakota, I believe, in the US. So this project has a layout on this, I believe it's a kind of ridge. It has 13 wind turbines, and in this case, these wind turbines are Vestas V90 turbines. And what I've prepared is a site compliance calculation, because I don't want to spend your time on going to site compliance, because I believe you all have licenses for site compliance. So I'll just briefly show you here. So we've did a calculation. So the turbine model is designed according to edition 3, and in this case we believe it's a class 1B, and I've set all the calculations up, and I've used WASP, and then you have this calculation here, and you see as indicated in the presentation, we see some exceedances here. It's actually quite green compared to what you'd often encounter, but there is some exceedance here for the wind speed distribution, because we have quite high wind speeds here on this side. So you see we have a significant exceedance here. So what we can do is that we can activate load response. That will be available if you have activated your license, and it'll give you an extra tab here. And then you can go in and you can define your generic turbine model. And in this case, the appropriate one, there are different options here, would be the one with a generic model with a rotor diameter equal to or larger than 90 meters. So we're just at the limit here. And if we were in a big hurry, we could simply just, and I don't want to include this just now, we could simply press calculate here to get the results. And we would get this overall result that all the components are okay, and I can see the worst index here. So that's the for the worst component for the worst turbine summarized here. We can dive into those results, and we can see the load index here on the y-axis as a function of the turbines, And you can go further in and see the details and zoom in here on the different components, see the load index for the different components, their Euler exponents. So if we wanted to look into the lifetime, because this is an older turbine model which might have been in operation for more than 10 years now, we wanted to investigate the potential for lifetime extension prior to maybe investing a larger sum in actual inspections. We could activate here, include DNV GL lifetime analysis. Because this is a generic turbine model, we need to quantify the uncertainty. And of course, this is not something that we can fully automate. We need some user input. So we've divided this into 3 categories. So you need to evaluate the similarity between the generic model used and the model for which we're doing this lifetime analysis. You can see a little hint here because this tells you that generic turbine models have a standard 3-bladed design with a standard nacelle and hub and a steel tower collective pitch, similar to reference turbine models like the NREL 5 megawatt. And in this case, we are calculating for the Vestas V90, which has exactly a setup like this with slender blades, standard nacelle, steel tower, and collective pitch. So in that case, we would evaluate that this has a high similarity. So that means in the low uncertainty category. We can go inside before we start the calculation here. And we can see that the DLC other here is included. That's a little bit more important when you're calculating lifetimes because it can change the results a little bit. So let's just do the calculation and have a look at the results. So now you see that fundamentally the graphics are the same as before, but now instead of showing the load index and this binary where the load index is below or above 100%, it shows you the lifetime. And you can go in and see which turbine has the best lifetime. So it shows per default the worst component for each of the turbines. And you can see we generally see lifetimes from 27 years and up. Again, we can also view this in this other graph here where we have the lifetime on the y-axis and the turbine number. We can see which turbine has the, you could say the worst lifetime here. We can again zoom into the table here and the detailed results. And we now see that we have the fatigue lifetime here, and we also have the standard deviation, that is the uncertainty on the fatigue lifetime indicated here as a column. And what we have now, because we have activated this DNV GL lifetime, we also have a separate tab for lifetime extension. It basically summarizes the alignment here with the DNV GL standard, and it summarizes the results down here. So we have 13 turbines, and the left box here shows you what is the worst component for the worst turbine. So it's turbine T30, and it's the main shaft, and it has a calculated lifetime of 27 years with a design lifetime of 20 years, and that leaves an expected extension potential of 7 years. And the quantified uncertainty here from using the generic model is slightly less than 2 years. On the right side, you see a histogram of the expected lifetime extension potentials here for all 13 turbines here, which ranges sort of between 7 and 10 years. So that's all good. What if we wanted to do this for a specific turbine model? Well, first of all, you need to have the file, and when you have the file, you need to place it in your windPRO data load response folder. And I have prepared a file here. I didn't have one from Vestas, so I made one myself. So I called the manufacturer EMD. But it's a specific model class 1B. When I place it in that folder, it'll appear here in my list as a specific model, and I can repeat the calculations here. I'll just clear my results, and I can go in, and I can see, yes, I have DLC other included, and I'll repeat the calculation. So it'll check for consistency between the turbine model for which I'm calculating and the information in this specific model. And it says, well, the name is different. Yeah, I know that because I called it EMD, and it's not called V90, but and the hub height is slightly different. But it's the right design class here. So let's just click OK here. Had it been a V90 model I've received from Vestas, we will not get these warnings. So it'll generally check for consistency here. And now we see the results, and we can see they have changed slightly. So this specific model has a little bit of margin for most components. And we can see in general here that the results have shifted a little bit. So now we have actually 10 years. So this additional margin has actually given us a little bit extra margin for the lifetime extension potential. But otherwise, you could say results are the same. We don't have the uncertainty estimate, as this is not required when you are calculating for a specific model. Yes, and I think with this, I will pass the word back to you, Per, and perhaps we have some questions.
Yes. So yeah, I will encourage you to ask questions in the chat box. So far, we don't have any questions, but luckily I have one for you, Lasse, which is you show a list of different generic turbine models. Which ones are available?
Yeah. So basically, what is available is what you see here. So this is a list we have extended over the years as part of our research. So you can say the most recent addition here is one for rotor diameters less than 60 meters. So that will actually be one which is often relevant for lifetime extensions. And then recently we've also added direct drive models or models where you have carbon in the blade. So that maybe you notice that the Wöhler exponents are different. They're up to 14 for carbon, so that's important to take into account. Of course, carbon is a more recent thing, so this is not so relevant for lifetime extension. There you would mainly be using the standard ones here. So generally, look at the rotor diameter, and that will help you decide which is the most appropriate of the generic models.
Yeah, so a question was whether we have a library of load response files of various turbines. And I guess these generic ones is the library that we offer.
Yes, this is the library. So the manufacturers will not, I mean, they are generally quite protective about their load information. So you can, there will be some manufacturers will be, in particular, if you make it as part of a tender where you're buying multiple turbines, they can provide you a specific model, but that will be on a project per project case, and you would need to consult them. So they will not make it generally available. Then you need to receive the file and put it in the right folder, and it'll appear here in the list just as my two specific models here. So yeah, reach out to your manufacturer, and if they are in doubt, I mean, they can also we'll be happy to facilitate the process. It is quite easy for them to implement new turbine models, and it's also very safe, as I described in the presentation.
Good. Then we have another question: whether you have stall wind turbines in the load response files.
Yeah, that's a very good question, in particular for the old models. We have looked into it, and we continue to do so. We don't have stall regulated turbines, and the thing is that in stall regulated turbines, they are very sensitive to the specific point of stall, and you will usually adjust the blade, the actual fixed angle of the blades, which will have a huge impact on the loads. So in general, the generic approach will not work so well. So you can, for specific turbine models, you can implement stall turbines, but so far we have not. We have decided not to include stall turbines. Yeah, we might do so in the future, but it's ongoing work, and we need to convince ourselves that it'll also be accurate enough, and we have not convinced ourselves about that yet. I mean, so the generic approach is very good for pitch control turbines.
Yeah, and another one, could you give an example for the different uncertainty options? Like, which are the usual deviations of the generic model to give a medium uncertainty?
Yeah, so that could be, I mean, I think you come a quite far away. So you could say this uncertainty is meant to quantify the uncertainty as an order of magnitude, right? So it's not like that it's nuclear or rocket science, and it's very difficult to quantify it. So basically, you need to look at the turbine model and then compare it to a standard design, as I indicated before, and you can see here. So it could be, for instance, an Enercon turbine, which has a concrete tower and a very different blade design, and also a very different nacelle design, which is very heavy. And that would typically end up in the high uncertainty category. And then you might have turbine designs there in between, which have either some differences in the design of the blade or in the tower, which will say, well, you have some deviations, but it's not across the board for all the components, and then in that case you would end up in the intermediate category. I hope that makes sense. So this is to capture the order of magnitude of the uncertainty.
Has there been any or perhaps confidential verification with results from in-house models from OEMs?
Yes. So we are not allowed to publish those for quite obvious reasons. Our manufacturers are very secretive about this, but we have done several comparisons, and that's also why I quite confidently can say that the generic approach works really well. It is, and I think we've seen manufacturers being quite surprised that you can take a generic model which even deviates quite a bit and still get accurate results, and that's for the reasons I described in the presentation. So the case where there will be differences that we cannot account for is these margins. So there can be arbitrary margins for a manufacturer. So in a way, you could say that the calculations that you do with a generic model will tend to be, or very often be, on the conservative side, because we don't know anything about the margin, so they are not included. But there could be and maybe this will be a slightly longer answer. Let's see if I can. We actually have a button here. So if you're a developer and you have a lot of interaction with manufacturers and you get a lot of load reports, you might actually gain experience with that. These particular models, we know that they have, say, 5% margin for a particular component. You can actually type that in here, and this will allow you to include this margin as a bias, and you can actually build that experience into also for your generic turbine models. This is something that we know is being used by different developers. That was a long answer.
And I hope that that answered the question whether there's an edit button to the load response details to test the change of some of the components. Or would that be a different approach?
Could you repeat the question, Pierre?
Yeah, well, the question is there any edit button for the load response details in order to test the change of some of the components? But I got a reply that you did answer it, so that's okay. That's good.
Otherwise, I can recommend, we have a quite detailed manual which also describes also some of these the design of the generic turbine models in quite some detail. So I'd recommend you to go to the loads manual.
Yeah. And then we have another question. Can we do calculations also with future neighboring turbines to see their effects on existing?
Yeah, you can include them in the calculation, but as it is right now inside the software, we cannot handle that you might have a certain period where you don't have the turbines and another period where you have the turbines. So there's some bookkeeping there. The bookkeeping is actually quite simple. So it's not very difficult to make the two calculations and then combine them, you could say, in Excel outside. And we're happy to support you in that. We have actually a small note that describes how you do it. So it can be done. But right now, the bookkeeping of the different periods, you would need to handle outside. But it definitely can be done, and we're happy to assist you.
And do you have any reference on real life case matching or not matching lifetime extension predictions?
I think it is very difficult, and as I also stressed that in many cases the real lifetime extension is driven by the inspection part, and the reason that turbine fails is not very often due to the fatigue, but due to other processes, failure in maintenance. And I think I didn't mention that, but this I mentioned that generally we need to go to the limit to have a feasible project. And in the old days, we were not as good in doing these calculations and designing the turbines. So generally, older turbines tend to have more margin, which actually gives a potential for lifetime extension. So I think that validation is very difficult, because in most cases the real lifetime would be determined by the other processes limiting the turbine lifetime, and not the fatigue.
Yeah. So that was all the questions. I have one more. I know that you're using this New Salem project, but perhaps you could show where do you get the TI from, the turbulence? Yeah,
it's true. When you download the sample, the turbulence data is actually not preloaded. So if you go into the Meteo object, you would need to go into the data and data setup, and then add the turbulence intensity signal here. You see I have already the data are there, but they're just not preloaded. So if you want to do that, you would need to go in and add it, and then load it.
And if you have another project with no turbulence data, what options do you then have?
Yeah, we with 3.5 we released this data set called GASP, Global Atlas of Site Parameters, which is fundamentally a big set of resource files, including all the siting parameters, covering basically the entire world. And you can download those if you go to Data and Siting Parameters, and you can download GASP. Per default, you'll download a map, which is 20 by 20 kilometers. It takes a little while because it's a lot of information. But you can see I already done that here, and I have a layer here. The resolution is 250 meters, so of course it's a little bit coarse, but it gives you all you need to do either a part calculation or a very early screening of the load. So you would simply, once downloaded, you would simply take the ambient site results, and then you would need to point to the site-res file that you download to your project folder. So that is what you need to do if you don't have any information from the site at all.
And then we have a question whether you have a plan to combine the turbulence values of NEVA in this process, into this process.
The turbulence values from NEVA. So I'm not quite sure. So to my knowledge, the turbulence values of NEVA are from the mesoscale data. And in general, I would caution you to use turbulence data from mesoscale data for load calculation. So they might actually match on average, but for loads, we need the 90% quantile as a function of direction and wind speed. And in general, there are big problems there for mesoscale data. They can't predict the standard deviation, and they generally tend to underestimate it significantly at higher wind speeds, which will significantly underestimate the load. So if it's the turbulence data from the mesoscale data you mean, we it is a deliberate decision that you can't base your load assessment on mesoscale data such as NEVA. But maybe maybe there's some NEVA data I'm not aware of.
Good. I don't think there's much more action happening in the chat box. So if you have any questions, fire away. You can also send us an email. Happy to do that, and we'll happily reply. I'll take the screen just for a second.
Yes, and I'd like to thank you all for the good and challenging questions. So that was very nice. So
if you need any support on the load response module or any other module in windPRO, for that case, you can always visit our help.emd.dk website, where you'll find the manual which Lasse spoke about and a quick guide. And this manual contains both the site compliance and the load response manuals. If you need further help, you can contact our support at support@emd.dk. For our German users, you can also ask for support from the German support office as well. We don't have much else. Let's close this early. Thank you very much, Lasse, for the presentation. I hope this was useful for all of you. Yes, so have a wonderful day, everybody.